This is the second video for the chapter Refraction, and I'm going to start off with something very important, very short but very important. These are conditions when you have incident rays going undeviated, or the path of the incident rays does not change when it travels through different media. The first condition is, say you have a glass block, or say you have any two media here. This is media 1, sorry, medium, not media 1. These are the two media, medium 1, medium 2. Let's do normal here, and this is of course perpendicular. Say you have a light ray that comes incident, it's incident like this. You can see that the angle that it's making is 90 degrees. An angle of incidence is the angle that it makes with a normal incident ray over here. So the angle between the two, you could see, is 0 degrees. So angle of incidence is 0 degrees. In these cases, the ray will not bend towards or bend away from the normal, because really it is normal. It is going in the direction parallel to the normal. So it will not change direction at all over here. It's going to go straight through, something like this. It's not quite straight, but it's going to go straight through without getting deviated at all. So you can say that the angle of refraction is also equal to 0 degrees. This is the first condition. Now, you also have certain substances whose densities, optical densities, are such that even though they might be completely different, one might be a solid, one might be a liquid, but despite that, the speed of light in them is very similar. So the refractive index, which we haven't studied yet, is also very similar. I know of one example that's you have Pyrex glass, specifically Pyrex glass. I think it has a refractive index of around 1.47 or 1.48, but you haven't learned that yet. And with that, you have cooking oil, which has, I think, again 1.47. So you have, let's say you have oil on the outside, and you have this yellow block here is your Pyrex glass. Now, if you remember, the condition for refraction, the cause of refraction, was that your two media have different speeds of light in them. But here, let's take that they have the exact same speed of light. So if they have the exact same speed of light, this whole thing is equivalent to just having a light ray passing through air over here and air over here. It's as if you're not even changing the media. So the same thing can apply over here. No matter how you take your ray, whether it's perpendicular like this, or it's at a very sharp angle like this, it's not going to get refracted or deviated. And the reason I just told you. But also note that oil, cooking oil, and Pyrex, even these two, they don't have exact refractive indices. Your indices can go up to, I think, 5 or 6 decimal points as well. So you're never going to get an exact match for two different substances. You're only going to get that for two same substances. Like here we took air and air, but what you need to know is very similar. So but in this case we're taking that the speeds are the same, really, not much difference at all. I'm going to move on to the laws of refraction, and then I'm going to introduce to you a few more terms. So the laws of refraction, there are actually two laws of refraction, but there's only one law, which is called Snell's law. Don't get confused in that. I remember I did, but only the second one out of the two it's also called, I think, the sine laws or something. But that is the Snell's law, but both the laws are the laws of refraction. The first one is simple. The incident ray, refracted ray, normal, and the point of incidence lie in the same plane. All that's saying is that if you have a glass block like this, say this is a side view, that means it's actually going on like this, something. Say this is your glass block, you're putting a ray onto it like this. So a normal, you could imagine, would be something like this, going through it like this. This is your incident ray here. And once it gets refracted, you can't really see reflection in this diagram because it's a side view, but it should be something like this. And then it'll come out again like this. So all we're saying here is that these points, the normal, the incident ray, the point of incidence over here, and the refracted ray, all lie in the same plane. It's not that your incident ray will come like this and suddenly your refracted ray will just jump out like this. They'll all be in the same plane. That's your first law. Your second law, the more important one, is Snell's law. What it says is that the ratio of the sine of the angle of incidence and the sine of the angle of refraction is equal to a constant for a given pair of media. And this constant ratio is called the refractive index of the second medium with respect to the first, and it's represented by the letter mu, the Greek letter mu, or also n. We'll come to that. But just to explain it to you first, I'll clear this up quickly. I'll just take your typical air to glass slab back to air example. So okay, that's a bit too much at the top. So here, this is your glass slab. Outside is your air. Even here there is air. You have a normal and you have an incident ray. It's coming like this. So the angle of incidence, you can tell, is this here. It's coming from rarer to denser. Remember that, rarer to denser, and back to rarer after that. So right now we're only looking at these two parts here, the first two. So it's going to come towards the normal, so it'll get refracted something like this. So I should draw the arrows here. So your angle of refraction is then this angle here, the small angle here. Now when this comes back out again, this is the emergent ray we're talking about. If you draw the normal again and we draw the emergent ray, it looks something like this. So the law says that the ratio, the sine of the angle of incidence, sine of the angle of incidence, that means sine I, ratio of this is to the ratio, the ratio of sine I to the sine of the angle of refraction. So that means sine R, and ratio means first one divided by the second. So what we're talking about here is sine I by sine R. Remember that I and R are both angles. You can take their sines. You would have learned it in trigonometry by now. Sine I by sine R for a given pair of media. In this example, we've taken air and glass, is constant, and it's called the refractive index of the second medium with respect to the first. Okay, right now we're taking only air to glass. We're taking this part of our diagram. So our second medium is glass. So this ratio here will be the refractive index of glass with respect to air. And remember that whenever you have any sine I by sine R or any refractive index of any substance with respect to air, that's called its absolute refractive index. Absolute refractive index. And easy way to remember refractive index, it just tells you the degree to which the light will bend in that medium. If you have the absolute refractive index of a certain any substance, whether it's glass or water or oil or whatever, if it's lesser, the light is going to bend lesser in it. If it's more, it's going to bend more in it. And another point here is that the refractive index of anything with respect to air or vacuum will always be, you'll see, it'll always be greater than 1. Why is that? It's because the absolute refractive index is basically equal to the speed of light in vacuum, we can denote it as C, upon the speed of light in that medium. This is it. This is the formula you need to know over here. And as you know, that the speed of light in vacuum or air will definitely be faster than whatever other substance you take. So since C is always greater than V, that means that this whole ratio will always be more than 1. Right? This V will never be more than it, so it'll never go into 0 point something, it'll be 1 point something, 2 point something. And refractive index of a medium depends on many factors, like it even depends on the colors, the light, the nature, physical conditions. That's all given pretty nicely in your book. You can look through that. But refractive index, you need to know these two things here. Firstly, sin I by sin R and C by V. This is for absolute refractive index. If you want the now, if you look at this, it's C by V, and C is, of course, the velocity in air. If we just compare it to our diagram here, and it's on V of glass. So you can see that it's actually equal to V1 by V2, where V1 is the first medium, and it's coming from V1 to V2. Also, the notation for this, we said, is mu. So what we write it as is mu1, 2. 1 is where it's coming from, 2 is where it's going to. So say from air to glass, we can write it as A over here because it's coming from air, and G over here because it's going to glass. So this is how you write the refractive index of glass with respect to air. And remember that any refractive index with respect to air or vacuum is always the absolute refractive index. Also, one more thing before I end this video is that whenever you come across sentences like the refractive index of this medium is this much, 1 point something or 2 point something, there you're always referring to absolute refractive index, unless and until they've given you the refractive index of this medium with respect to this medium is this much. You have to assume that it's the absolute refractive index, and they're taking the first medium as air. So now I'm going to continue this in the next video, so I'm running out of time.